I want you to picture the exact moment right after you finished a really, really good meal.
Oh, yeah, we all know that feeling.
Right. Maybe it was a huge Thanksgiving dinner or,
Ah,
just a massive burger and fries on a Friday night. You put the fork down, you lean back in your chair, and you let out that heavy sigh.
it's the universal sound of just being done.
Exactly. You feel heavy, you feel slow. Honestly, you probably feel like your brain is just shutting down for maintenance.
Yeah.
But here's the thing that absolutely blows my mind, and it's what we are digging into today. While you are mentally checking out, your body is essentially responding to a five-alarm fire.
It really is. I mean, it's the busiest shift your body is going to work all day. We tend to think digestion is passive, like food goes in, your stomach gurgles, and, energy comes out. Simple.
But it's not passive at all. It's this incredibly aggressive, high-speed logistical operation. And today, we are doing a deep dive into our source material, which is a breakdown from Metabolism Made Easy. Specifically, we're looking at a section titled Insulin's Tissue Effects Stimulatory and Inhibitory.
Right. And our mission here isn't just to talk about blood sugar in a general sense, because if you just stick to the high school biology line that insulin lowers blood sugar, you really miss the elegance of the whole system.
Yeah, we are unpacking the specific mechanical levers insulin pulls, because the source material frames insulin not just as a cleaner sweeping up sugar, but as a master switch that fundamentally changes your body's operating system from fasting mode to fed mode.
Exactly. And it does this by coordinating dozens of different departments, like your liver, your muscle, your fat, and giving them all different orders at the exact same time.
It's like a manager shouting orders. But the source highlights that the orders are highly specific, depending on who is listening.
It's the difference between a general just randomly shouting charge and a conductor leading a symphony. If the timing is off by even a fraction of a second, the whole thing falls apart.
So let's set the stage for you. The source starts the clock the exact moment the meal is consumed. You've eaten the burger. What is the very first domino that falls here?
The initial trigger is the rise in plasma glucose. So you digest the food and sugar starts flooding into your bloodstream. Now imagine your blood is essentially getting thicker, sweeter.
Almost syrup-like, which sounds terrible, by the way.
It is terrible if it stays that way. That state is actually toxic. So floating in your pancreas are these little clusters called beta cells. Think of them as the sensors. They are constantly tasting the blood flow.
Okay, so the beta cells taste the sugar spike.
And they react with absolute precision. They immediately release insulin into the bloodstream. And this is where the magic really starts. Insulin travels everywhere. It's a broadcast signal sent out to the entire body. But, and the text makes a crucial distinction here, not everyone is listening.
Right, I really like that part. It's like a radio frequency that only certain radios are tuned to pick up. The source lists three main listeners, or target tissues. Who are we talking about?
The big three are the liver, muscle, and adipose tissue. And adipose is just the scientific term for your body fat.
Okay, so the manager insulin has entered the building. It's got a megaphone. Let's walk through this department by department, starting with the liver and muscle, because the source groups these together when it comes to handling sugar.
They are grouped together because their primary job in this specific moment is the same: get the glucose out of the blood. The source calls these the stimulatory effects. Essentially, insulin is telling these tissues to open up and consume.
But consume can mean a couple of different things, right? It's not just, eat it and be done.
Correct. And this is where people often get tripped up. Insulin actually stimulates two distinct processes here. The first one is glycolysis.
Glycolysis. Okay, break that down for us.
Sure. Glyco for glucose, lysis for breakdown. This is burning sugar for immediate energy. It's like taking logs and throwing them directly into the fireplace. The liver and muscles start grabbing the glucose and burning it instantly to power their own machinery.
Wait, hold on a second. If I just ate a massive meal, I have a total surplus of energy. Why would my body start burning it immediately? Shouldn't I be saving it? It feels kind of counterintuitive to burn the supplies you just got.
That is a great question. It's really about prioritization. Your body is always running. Even when you are just sitting on the couch, your liver is working, your heart is beating, your muscles have tone. By switching to burning the incoming glucose right now, you spare your other fuel reserves. You stop burning your stored fat and switch to the free energy that just arrived at the door.
Ah, okay. So you use the cheap stuff while it's freely flowing.
Exactly. But you can only burn so much in the moment. You're sitting in a chair, after all. You aren't running a marathon. So once the immediate energy needs are met through glycolysis, insulin triggers the second process, which is glycogenesis.
Glycogenesis, genesis meaning creation.
Yes. The creation of glycogen. Glycogen is just long chains of glucose packed together really tightly. It's the storage form. So the order is basically burn what you need right now, and whatever's left over, pack it into boxes and stack it on the shelves.
Burn it or bank it.
That is the go signal. But here is where the source material gets incredibly insightful. If we only focus on what insulin turns on, we are missing half the story. The source places a huge emphasis on the inhibitory effects. What insulin turns off.
Because you really can't do everything at once.
Well, think about it from an engineering standpoint. If you are trying to fill a reservoir with water, what is the very first thing you have to do?
Make sure the drain is plugged.
Right. It doesn't matter how fast you pump water in if the drain is wide open. You are just cycling water through. In biology, we call that a futile cycle. It generates heat, it wastes energy, and it literally accomplishes nothing.
So while insulin is shouting to store the sugar, it must also be simultaneously shouting not to release any sugar.
That is the exact logic. The source lists two specific things insulin inhibits in the liver. First, it inhibits glycogenolysis.
Which is the exact opposite of what we just talked about.
Right. Glycogenolysis is the breakdown of those stored boxes of glycogen. When you are fasting or sleeping, your liver breaks down glycogen to keep your blood sugar stable. But when you have just eaten, insulin slams the brakes on that process. It locks the warehouse door.
Okay, so absolutely no taking from the reserves.
And secondly, and I think this is really cool, it inhibits gluconeogenesis.
Gluconeogenesis, breaking the word down, that's glucose. New creation. New glucose creation.
You've got it. The liver is this amazing chemical factory. It can actually take waste products, amino acids, things like that, and build brand new glucose molecules entirely from scratch. It does this when you are starving.
But if I just ate a giant bagel...
You absolutely do not need your liver manufacturing more sugar.
Yeah.
You are drowning in sugar. It would be like a factory printing more inventory when the warehouse is already overflowing. So insulin goes into the factory and physically shuts down the assembly line.
So the real takeaway here is that insulin isn't just a storage hormone. It's an efficiency manager. It prevents the body from working against itself.
It creates a one-way street. Glucose goes in, nothing comes out. That is the only way to clear the blood quickly and safely.
Okay, I want to pivot to the mechanics of how the sugar actually gets in, because the source has this whole section on the mechanism of uptake for muscle and fat. And honestly, I always just assumed cells were kind of like sponges. Like, if sugar's in the blood, it just sort of naturally soaks into the tissues.
A lot of people think that, but if cells were like sponges, you would be in big trouble. You couldn't control what gets in or out. Cells are much more like fortresses. The walls, the cell membranes are generally completely impermeable to sugar. It bounces right off.
So the door is locked.
The door isn't just locked, the door isn't even there.
What?
In muscle and fat cells, in the resting state, there are no doors for glucose on the surface. They're effectively sealed, completely shut.
So how does the sugar get in? The source mentioned something called GLUT4.
Right, GLUT4. These are the transporters. Think of them like specialized revolving doors or turnstiles that allow glucose to enter. But here is the catch. When your insulin is low, all those GLUT4 transporters are hiding.
Hiding where?
Inside the cell. They are sequestered in these little vesicles floating around in the cytoplasm. They're kept in storage.
Okay, so the cell has the doors, but it keeps them down in the basement.
Perfect analogy. Now, insulin floats by in the bloodstream and basically rings the doorbell. It binds to the insulin receptor on the outside of the cell. That signal sets off a chain reaction inside the cell that says, go get the doors.
And they physically move.
They physically move. The vesicles carrying the GLUT4 transporters travel up to the cell membrane and fuse with it. Suddenly, where there was just a solid wall, now there are thousands of open gates.
That is wild. It's literally remodeling the architecture of the cell in real time.
It's known as translocation. And it happens within minutes. The moment insulin drops, those gates pinch off and go right back into the basement.
So when we say insulin helps sugar enter the cell, we aren't talking about it politely holding the door open. We're talking about it forcing the cell to install the doors in the first place.
That is the level of control we are talking about. Without insulin, muscle and fat are essentially blind to the glucose floating right past them. They would starve in the midst of plenty because they simply can't install the gates.
That puts a whole new visual on things. Okay, so we've covered the sugar. Liver and muscles are soaking it up, burning it, or storing it. The GLUT4 gates are wide open. But my meal wasn't just sugar. we have to talk about the other side of the coin, the fat.
The lipid switch.
Right, because if I ate that burger, I've got fat circulating in my blood too. Does insulin care about that? Or is there a totally different manager for fat?
Oh, insulin definitely cares. Insulin is the master controller of all energy storage, not just sugar. And the source details how it handles the adipose tissue, the fat cells, specifically regarding dietary fat.
So what are the orders for the fat cells?
Well, first we have to get the fat inside. When you eat fat, it doesn't just float freely. It travels in these microscopic spheres called chylomicrons.
Chylomicrons. That sounds like a Transformer villain.
It really does. They are basically little oil tankers floating in your veins. Now, the fat cells need to unload that oil. So insulin cranks up the production of an enzyme called lipoprotein lipase.
Lipoprotein lipase. Try saying that 5 times fast. What does it actually do?
Imagine the fat cell is a building, and the blood vessel is the street outside. Lipoprotein lipase is like a crane or a grapple hook that sits on the wall of the blood vessel.
Okay, I am picturing the claw game at an arcade.
That is actually a brilliant comparison. This enzyme reaches into the passing chylomicrons, grabs the fatty acids, and physically pulls them out of the blood and into the fat cell.
And insulin is controlling the claw.
Insulin gives the fat cells the budget to build more claws. It stimulates the expression of lipoprotein lipase. More insulin means more claws, which means you clear the fat from your blood faster and stuff it into the fat cells.
And once it gets in there?
It gets reassembled into triacylglycerol. That's just the scientific name for the stuff that fills up a fat cell. It is your long-term energy savings account.
Okay, so that is the go signal for fat. Build the claws, grab the grease, store it away. But going back to our theme of the double switch, the on and the off, does insulin stop fat breakdown too?
It has to. And honestly, this is the most technical part of the source material, but it's also the most important for understanding why it is so hard to lose weight when insulin is high.
Okay, walk us through it. The source mentions an enzyme called hormone-sensitive lipase.
Yes, hormone-sensitive lipase, or HSL.
In plain English, what is this thing's day job?
HSL is the fat burner. It's the enzyme inside your fat cells that chops up the stored fat so it can be released back into the blood for energy. When HSL is active, you are losing weight. You are burning your reserves.
So naturally, if I just ate a burger, insulin wants to kill this guy.
It wants to completely incapacitate him. But the how is just beautiful chemistry. The source describes the mechanism as dephosphorylation.
Dephosphorylation. Okay, we definitely need to pause here. That sounds like we are diffusing a bomb. What is happening chemically?
Think of enzymes like little machines. Some machines have an on-off switch. In biochemistry, that switch is often a phosphate group. It's just a little chemical tag. For HSL, when it has that phosphate tag attached to it, it is on. It's buzzing, chopping up fat, doing its job.
So phosphate equals on.
In this specific case, yes. So insulin comes along and triggers a process that rips that phosphate tag right off. That is dephosphorylation.
It literally steals the battery.
Or it effectively breaks the key off in the ignition. When you remove that phosphate group, the HSL enzyme physically changes shape. It becomes completely dormant. It cannot chop up fat anymore.
That is incredibly specific. It's not just blocking the door, it's going into the engine room and dismantling the machinery.
Exactly. And this is why the source emphasizes the inhibitory nature. As long as insulin is high, HSL is dephosphorylated. It is chemically impossible for your fat cells to release energy because the machinery to do so has been totally disabled.
Which perfectly explains why you can't burn fat and store fat at the exact same time.
You physically can't. The signals are mutually exclusive. You cannot have the storage hormone and the release enzyme active at the same moment. Insulin ensures that by chemically modifying the enzyme.
It really highlights how absolute insulin is. It takes full control of the entire metabolism. It isn't a suggestion. It is a mandate.
It is a total lockdown. Just think about the sheer coordination we have just covered. Step 1, tell the liver to stop making sugar. Step 2, tell the muscles to build doors, the GLUT4, and take the sugar in. Step 3, tell the fat cells to build claws, the lipoprotein lipase, to grab the fat. And step 4, go into the fat cells and chemically disable the fat-burning engine HSL.
And all this happens in the span of, what, 20 minutes?
Minutes, every single time you eat. Whether it is a massive 5-course meal or just a Snickers bar, this entire fleet of biological responses deploys instantly.
It really puts that food coma feeling into perspective. My brain might be checking out watching a movie, but my cells are running a high-stakes logistics center.
They absolutely are. It is an efficiency machine. And the goal is always the same: safe storage. Because in nature, you never really know when the next meal is coming. So when food arrives, the body does not waste a single calorie. It locks it down tight.
I think what stands out to me most from this deep dive is the mechanical precision. We hear the word metabolism, and we just think of it as this vague cloud, like, oh, I have a fast metabolism. But it's not vague at all. It is literal gears and levers. It's move this transporter, remove this phosphate.
It is biological engineering. And understanding these mechanisms, glycolysis, glycogenesis, lipolysis, it takes all the mystery right out of it. Your body isn't fighting you. It is just executing a program, a very, very old program designed to keep you alive.
So we've spent this whole time looking at the on switch, the fed state. But as we wrap up, this leaves me with a burning question for you to consider.
What is that?
Well, the source detailed exactly how insulin acts as the manager for the fed state. It implies this perfect synchronized order. But that implies there is an equally complex scramble that must happen the exact moment we get hungry again.
Oh, absolutely.
Like what happens when insulin actually leaves the building? All those GLUT4 gates have to close. The factory in the liver has to spin back up. The HSL enzyme needs its phosphate back.
That is the beautiful chaos of the fasted state. The off switch for insulin is the on switch for survival. Glucagon, cortisol, adrenaline, they all come out to play.
It sounds like a much more stressful day at the office.
It is a chaotic story, but definitely one for another deep dive.
Indeed. Until then, I hope you appreciate the incredible work your body is doing while you simply digest your lunch. Thanks for joining us on this deep dive into metabolism.
Stay curious.